course. Yeah. Without any sleeping. That is a problem. I'll fall asleep. I think I understand. Yeah. If I do, I become it.
Okay, shall we assume everyone is here? Awful weather out there. Yeah. Okay, so we are in the section of portfolio optimization, the first topic we want to talk about. And we talked about the mean of a portfolio, the variance or standard deviation, which we are going to interpret as the risk of a portfolio. And we learned that there is an efficient frontier. We learned how to calculate this equal corners and calculate points on this to understand what this thing is about. Okay. There was a question earlier from someone that in the lab sheet that I gave you, I said generate at random 100 portfolios, compute their mean and variance, and plot them along with the efficient portfolio as scatters. Yeah. So you can very easily generate a random portfolio. It's just 3 of these, so 3 random numbers, but they should add up to 1. Yeah. So you can, I know you know how to do this. You can do this. So you generate 100 3 vectors which add up to 1. Run the portfolio, compute V and M, and put a point for each of those 100. Yeah. All you will find is that based on those 100 that you generate, these points will be here, they will never be here. Okay, so this is just, I just want you to have a picture of this. It's simple. Okay. I think because many of you who were on the machine learning course are familiar with this tool, but some of you were not, and I'm not allowed to assume that you have done the machine learning course. So those who were not on the machine learning course, are you all comfortable with downloading, setting up CBX, running one of the example papers, example problems in it? Yeah, so this has to happen, right? Otherwise I'm in trouble. Yeah. Okay, so I'm going to assume that all of you are comfortable with running this. The next one is the harder task. You should know exactly what's going on here. That's part of the exercise that you're doing. Okay. Okay. So that's what we did was we talked about that mean variance portfolio that I was trying to draw here, and we looked at this paper, Brody's paper, which appeared in 2007, talking about sparsity, inducing sparsity into that, which is part of the exercise you're doing. Okay. That paper, I think I mentioned this on Monday, has a little bit of difficult part that goes into how they implemented the optimization algorithm. Okay. We are not going deep into that. That's the lasso algorithm with constraints. They're solving it in a particular way. It turns out because it's a convex optimizer, we can use this tool to solve this, so we are bypassing that. Okay. But of course, you're welcome to read about lasso and how they implement this. It's great fun. It might be useful in life at some point. Okay, so we want to look at another paper. This is Lobo et al. And I'll give you the precise reference and in the slides. These guys tell you how transaction costs might happen, how they can also be integrated into the mean variance optimization framework when you select a portfolio. So all we will see is what are sensible ways in which you can specify that kind of cost that you incur. How can you plug that in while you do the optimization of minimizing risk while maximizing profit and so on. Okay? And then we will restrict ourselves to formulations that happen to be convex optimization problems, and you can solve them very easily. There are some formulations which cannot be shown to be convex, therefore you need much more powerful machinery to solve them, but that can also be done. Non-linear optimization is a well-developed area. But if you stay within the convex optimization framework, the tool that we have will work. It's a very elegant, well-structured way of doing it. Okay? So now comes the disaster. When I start picking material from different papers, they keep changing the notation. Yeah? So in this course, I'm not going to reset the notation. I'm going to expect you to read the paper a lot. So I'm going to stick to the same notations that the authors use as much as possible. So this was our pie. So the portfolio consists of weights and the returns. This was our R in the past. Returns are going to be called A in this nice language. And then we know there's an expectation of these returns. We're going to call this A bar. And there's an expectation of the matrix times matrix transpose after you have taken away the mean. That's the covariance matrix. Okay. I've said this before, try and follow algebra like this with linguistic descriptions as much as you can. Yeah. So I never look at this as algebra, I look at this as data, take away the mean, multiply by transpose, that's like squaring, and then I'm going to take the expectation, I'm going to average over all the data I have, that's what I understand by covariance. Okay. How do things covary when you integrate over the entire space? So we're going to look at problems, because we're going to look at transaction costs, we're going to look at problems where you started with some portfolio in which you have invested your money, and then you're going to take a small perturbation to this. You're going to adjust this portfolio by a value x. Okay. So the new portfolio is going to be called W plus X, and the wealth you have associated with this is A transpose, that's a return transpose times W plus X. Okay. So that's exactly the notation redefined again in X and W's. Yeah. So we're going to look at mechanisms by which we know that the transaction cost will be associated with what you change to what you have, and how can we, for example, minimize transaction costs, or subject to allowing a particular amount of transaction cost, maximize the wealth that we're going to reach. Yeah. Okay, so again, notations, we know the portfolio return. That's the average return transpose your perturbed investment. The variance on this, which is something that we have seen before. Okay, so this portfolio will have a mean and a variance. Okay, so transaction costs, of course, we can write this as some function of the disturbance that we have made, or the transactions that we have made. We will then start about talking about a budget constraint. So what we are saying here is that the sum of all the monetary value of the transactions that we have made. So we have an asset which has some value, we buy a little bit more of this, by how much have we increased? Yeah. We will do that on all the n assets, and we sum up all the transaction costs that we have, sum up all the wealth change that we have incurred. We add to that, on each of those transactions we would have paid some money. And that total is going to be negative. Why is this going to be negative? I'm going to assume that I'm not going to input any more money. Yeah. I have a particular wealth in terms of portfolios. I'm going to sell something, buy something, and so on, with the hope that my new adjusted portfolio will give me better yield. Yeah. But I'm going to pay for that by whatever I sold and bought, or whatever I gained by selling, take away whatever I lost by what I gained by selling and what I lost when I bought something, and when I add them up and I paid this, and if it's equal to 0, then that means I have not incurred any loss. I guess I've balanced it perfectly. Okay, so what kind of optimizations one could do in this? So like I said before, you can ask the question, I want to maximize my profit, not profit but my wealth at a particular period of holding this investment, subject to this transaction cost being negative. And that the solution that I get is in some feasible set of solutions. So this is written very generally here, but we can expand on this. we'll see a little bit later, we can impose constraints like, again, we have seen these constraints like, constraints on short selling, constraints on the variance and so on. Somehow, all these optimization problems we look at will have the structure. You want to maximize something subject to some conditions that you can write down, and those conditions plus other conditions will form a feasible set of solutions. Yeah. So that's one way of thinking about it. The other way of thinking about it is to say, I want to pay minimum cost of making this readjustment to my portfolio, subject to achieving at least a certain amount of return as a result of doing this. Okay? So both are sensible things to do, and that's the sort of thing that people would do. What would these transaction costs look like? So it may be usual, you can assume that they are independent on every stock you might incur transaction cost, you can add it up. That's a usual assumption in the literature. You might imagine this being violated, some exchange might tell you if you buy this and this, I will give you a discount on buying something else. Yeah, so they could be correlated, but that they are separable is one convenient assumption that you can make. You can make the assumption they could be linear in terms of how much you have bought or sold. Yeah. So you can think of saying that this transaction cost on the ith asset is alpha I plus times xi. If you change xi, if you buy xi, then that's positive, and there is a certain slope with which you pay. The more you buy, the more you pay. Yeah. When you sell, the more you sell, the less you pay. You tweak a minus in, yeah, so that you can treat everything as an additive thing. Okay? So if you did that, okay, so this turns out to be a convex function. The shape of that graph would look like this. In the x space, it's not here. X plus will have a slope. X minus need not have the same slope. Okay, so that slope is alpha I plus. This slope is alpha I minus. So a function like that, even though there's a discontinuity here, will result in a convex cost function and can be solved very easily. One can think of a transaction cost that has a linear term and a fixed term. Yeah? It is shown in the literature that that one is not convex, so that might look a bit like that. So we can have a beta I plus, a beta I minus, alpha I plus as slope, and alpha I minus as yeah. So if we model transaction cost like this, this is actually more likely that you will have a fixed cost plus a variable cost. Literature shows that this would be non-convex because of this sharp jump here. Okay, we're not going into understanding why something is a convex program, something is not. We'll just take the word for it from literature. Okay. But it may well be that you want to work with the convex set, then maybe you're working in situations where this is negligible with respect to that. Then you might say, okay, I'm going to set this to 0 and just work with this one and optimize it, and then maybe at the end of it make some adjustments. There are, in a lot of these things, you start with some sensible specifications, translate it into some mathematical language, turn the handle with an optimizer and solve it, and then make, of course, sensible adjustments towards there. Yeah, so that's loop you will see almost everywhere. Okay, so what are other types of constraints we can think of? We can limit the excessive diversity in this. So we can say, for example, that after I perturb or adjust my wealth in one of them, the resulting investment should be bounded by something. Yeah, so I might say that whatever the optimizer gives me, I don't want to invest too heavily on one particular asset. On any asset, I might say I want to limit this. This is a simple way of doing it. Or you might say that the perturbed wealth in any asset, your exposure in any asset, should be some less than some fraction of the total wealth. There is a term missing here. Okay. So the paper, when you read the paper, you will find it will be Wi plus xi less than equal to some gamma times 1 transpose So you must know that I prefer teaching by writing on the board, but I get told in student evaluations this guy doesn't give notes. So now I'm trying to shift to that. Right? The advantage of doing this is if I forget to write the gamma, then there is no evidence. When I rub the board, it's gone. But now this is a little bit more careful here. So if you spot errors, you have to shout, okay? So that next year we'll do it. Okay, so another way is you might imagine that you might limit the exposure to any small group of assets. You might say that R of these assets that I have as a group, I don't want to spend too much on this. I don't want to invest too much on this. So that will look like this one. Again, there is a gamma here. That the sum of WISI over these R terms over some i's that I specify. I'm going to say this one, this one, this one. The total investment that I spent on that has to be a fraction of my total wealth. That fraction is going to be a missing term. Okay. If you read the paper, this paper you will find, this one there, that this one is a little bit tricky, but this is convex, and they go into how you actually show that this is convex. The constraint I have written here is sum over R assets out of N assets. And they tell you how you can write this expression as all the possible combinations of R choose from N, and all of them would be convex individually, and the combined union would be convex, so this is also solvable very easily. Yeah. So again, sensible little things you can think of as criteria you might impose when you adjust your portfolio results in expressions that we can actually plug in, turn the handle, and so on. Okay. Short selling is another one. Okay, so again, I can just write that the perturbed value should not exceed minus SI. So SI would be in asset I will have a negative exposure. A negative exposure means I've borrowed from someone a certain number of Southampton University's assets and sold it to you. Yeah. So at some point you will come for it. Yeah. You will say you want it back. Then, well, this guy wants it back. Then I have to buy it and sell it back to him. Yeah, so that's what owning something negative means. So short selling is you have sold something that you don't own. You have borrowed to sell. Or of course you can say the sum of all the exposure, all the short positions should be less than some upper bound, so that you can be safe, that you don't have this guy come to you and you are unable. Collateralization is an issue. So you might have a constraint like this one, that is your sum of all the short positions, yeah, so those are the negatives, should be less than a fraction of your positives. That's the stuff that you're holding. Yeah. So this is like, you borrow money from the bank. What do? You say, I want to build a house. I tell the bank, give me a certain amount of money, and here's the house that you can keep as a collateral. Yeah. What that means is if I don't pay the bank, then the bank will take my house away. Yeah. So here, this is the money that I have, the equivalent of the money I borrowed from the bank, because I have borrowed this much stock to short my position. Yeah. And if they come for it, then I have to pay it back. Right? So I might want to have a situation that I have at least as much as this positively owned. Yeah. So when I have to pay back, I can just give it back. So I can impose a criterion like this and then optimize against these W, against the X's, to satisfy this kind of a constraint. Okay. It gets a little bit more interesting now. So we have seen this before. We might want to reduce the risk. We have seen this expression before. Your asset transpose covariance matrix asset is the variance of your portfolio. You might want to limit this one. You will agree I can write this in this way. It's a norm of, if I take this matrix sigma, if I can write the square root of this, the square root is not square root of the individual components. I'm going to say that I have a matrix A. My square root is, I'm going to write A to the power half. That means A to the power half transpose times A to the power half is going to be A. Yeah, it is not, it's matrix multiplication. It's matrix square root, not individual element-wise square root. So what do we have here? This is a number. It's a vector transpose matrix. Vector is a number. this number should be smaller than some variance that I want to have. Yeah. This one, this is a matrix, that is a vector, the product is going to be a vector. The norm of that vector is a number. Okay? So if I had this situation, so if I had, think about x transpose AX, yeah? And this A is going to be now A to the half transpose A X. X transpose. Yeah? If you think of this much as some Y, you can write this as Y transpose Y. Yeah? That's just the same as the norm of Y. Okay? So that's the structure you should have in your mind when you look at that. Yeah?
So is A to the half the same as the Cholesky factor?
Sorry?
Is that the same as the Cholesky factor?
You could use Cholesky factor there. Yeah. Yeah. Sorry?
Should be to the power. Yeah, to the power of 1 and the square root of A as well. The second A.
Over here? Below?
One you're not transposing hasn't got a power.
Oh yeah, okay, yeah. So yeah, sure. Sorry.
This one and, yeah.
Okay. But the interesting thing about writing it this form is it turns out it will be seen as or described as a second order cone constraint. What this really is that norm of a vector bounded by something. So think about that vector as y consisting of y1 and y2. And if I write square root of y1 squared plus y2 squared should be less than some t, then that is a constraint that looks like that. That my feasible solution should be here. So if I write the norm of some vector y is less than t, which is what I'm trying to draw here, that will be that. Yeah? But if I move t, make it higher and higher, then my constraint would grow when the surface large. Yeah? So it's a conical constraint. It is also known to be a convex constraint, and you can solve this by convex optimization problems. That's why it's interesting to look at it this way. Now comes another one. This is much more interesting. This relates to what we saw as value at risk. I can ask the question, instead of saying I want to minimize the variance, I might set a bar on my wealth, and I might say that the chances of my wealth being higher than some threshold should be very high. Okay? So imagine this eta is, I don't know, 0.9. So I'm going to say I want 90% confidence that my wealth as a result of this investment being higher than some minimum wealth that I have, will be higher than some minimum wealth I have. Okay? I can easily write this. So remember, just the same way, we said when we said minimize the variance, we say there is a distribution, that should be a narrow one. Yeah? What we are saying here is there is a distribution, the area under the curve above W low, above some threshold, should be that. Okay, so I'm going to bound the area, bound a certain probability. Okay, so this one I can, but we know that this W has is computed like this. This is a normal distribution, mean and variance. And what I have written here is this one. I believe this is correct. I drew this picture last night. I'm not, because you guys say I should draw pictures like Adam Krugel there, so I'm trying very hard. So what it is, there's a normal distribution with mean, mu, and variance sigma, sigma squared. And I'm going to say that my wealth W, which has this normal distribution, has to be higher than W low, and the probability it will be higher than W low should be that area, and that area is going, I'm going to specify. Okay, so I want to be 95% or 80% confident, but this looks more like 80 than 95, 80% confident that the wealth that I have will be higher than this threshold. Okay, let's see how this translates algebraically. I can rewrite this one apparently in this way. Okay, so let's see if this is true. So what I have is wealth being greater than W. I can And if you have done some statistics a long time ago, we have the normal distribution with zero mean and standard deviation 1, tabulated, graphs drawn, you can look it up. Yeah. If you have an arbitrary normal distribution with some mean and sigma squared, you do a change of variable, and the change of variable you do is subtract the mean and divide by sigma. Yeah. And in that changed variable, you will have a normal distribution. Yeah. So that's arbitrary Gaussian, this is not, and 1 is a normal distribution. So when you plug it into normal distribution, then you can look up area under the curve, similar to this one. Simple. Okay? Okay. So, very, very good. So what I have done here is I have written this area. Hopefully I have done that. So my wealth being lower than the threshold, yeah, should be smaller than that area. Which is the same as saying my wealth being higher than that should be bigger than this area. Is this correct or wrong? Whether this is correct or not in this kind of environment can be more easily judged from the back of the room than standing here. Okay? So, happy? Okay, let's say this again and see if this works. So the probability that my wealth is bigger than some threshold should exceed what I have specified. Okay? Then that means the probability my wealth is below that threshold should be smaller than 1 minus what I have specified.
Should be straight plus sign.
Okay, yeah, the equal sign, if I were a pure mathematician, I would worry, but computer science, right? So fixed floating point arithmetic, right? So you will never have equality, so for us. Okay, so yeah, okay, so this scale variable, I think people refer to this as Z normally. Yeah. Is between 0 and 1. Sorry, it's not between 0 and 1. It's a normal distribution mean 1, 0, and standard deviation 1, or variance 1. So what I can then say, therefore, is that I can write that probability that I have as the cumulative normal density evaluated at, cumulative distribution, or cumulative normal distribution evaluated at that number. Okay? So the cumulative distribution integrated from minus infinity to z is this area. Integrate from minus infinity to this one with respect to an auxiliary variable, then you have this area. So I drew a picture for that. I must show you. No, that'll come in a minute. So of course, so I can rewrite the condition that I had in the previous thing as that this scaled variable should be smaller than the inverse of this function. Okay, evaluated at this 1 minus eta, which is at the threshold that I'm setting. And the next step, of course, is to look at this argument, that the inverse of this function at 1 minus eta is minus of the inverse of it at eta. Okay? And this is where I drew a picture for you. I'm quite pleased with this, so you have to see this. So you're happy with this curve is my phi function, which is the cumulative probability. Yeah? It has to go from 0 to 1 as you go from minus infinity to plus infinity. At some probability eta, which is what I have specified, yeah, the inverse of this function is here. Yeah? At 1 minus eta is here. And this distance and that distance are the same. Okay? So you take this function, chop it, reverse it, and flip it, you get it. Okay. So that little algebraic trick will give us a condition that says that the mean of my portfolio, given the return distribution, and the standard deviation, or the standard deviation here, is going to be related by this condition. So mean take away, what am I doing? Mean take away what I specified, eta is something I specified, sigma comes from the portfolio's properties. I have written a little condition, which is a restatement of the probability condition that I started with. But that's all I have done. Yeah, I said my wealth being bigger than a threshold should be confident this should happen. And that probabilistic statement translates into an inequality like this, all of which I can look up. Yeah, so when you look at this, you know that W low is what I specified. This comes from the properties of my portfolio behavior. Sigma comes from the properties of my portfolio behavior. This is the inverse of the cumulative density function, and this eta also something I specified. Okay. So that translates into, so now mu and sigma we know, so plug in mu, plug in sigma, I get an expression in terms of this one, this one, this one, this one. Yeah. Looks a little bit horrible, but it's a restatement of what I wanted to achieve here, given Gaussian distributed mu sigma overall mu capital sigma as covariance matrix profile stocks. Okay, so that's where we end up, and that's okay. So now, why is this a little bit cool? So what I have here is the statement that the probability my wealth should be greater than or equal to some, should be at least eta, no sorry, it should be greater than eta, translates into this condition in terms of all the variables I have. Yeah? In this one, I know this is my expected return, this is my variance. Yeah? The expected return and variance are the terms that we were looking at in the portfolio optimization problem. Variance here, expected return mean here, the mean variance problem. Yeah? And we were saying with this picture, in this space, some points are realizable, some points are not realizable. Yeah? What would this constraint look like in that space? What would be points in this space that will satisfy this constraint? So we can think about it this way, right? So in this space, when we introduced the Markowitz portfolio, I said, given Gaussian distributed random variables and so on, not all points in this are realizable. Only some of them will be realizable, and we calculated that efficient frontier. We have exactly the same thing here. We specified a condition in terms of probabilities. We said I should be able to score at least that much. And we said making that claim is exactly this statement, making this statement. Yeah? And in this statement, we have variance here, mean here, and the W low that we went and plugged in, and the probability that we plugged in came out this way. Yeah? If you think about this one, you will see that this phi eta is just some constant. Let's call it a small m, because as soon as I specify this, this is fixed. Yeah? This one is the variance that I have on this axis. Yeah? Let's ignore the inequality and just say equal for the moment. Yeah? This one is my, I should not use m here, because it's a thing to do. Let's call it, I don't know, alpha. That one is my mean here, correct? Minus some constant. That also I specified. Yeah? So that's a straight line, right? In this VM space, that's a straight line. Yeah? So what that means is that there is going to be a line like this, and my expectation that I specified in terms of probability is telling me that I can achieve some points here, but I cannot achieve points here. Correct? So my constraint can be mapped in this mean variance space. Yeah? And on the same thing, if I plot for this particular portfolio the efficient frontier, that's going to look like this. Yeah? So the efficient frontier is subject to this probabilistic specification of how much wealth I want to have, how much confidence I will have that the wealth will not go below W low, gives me an operating point, which is this one. Yeah, that's where I would put my money. Are you with me? And there is a picture somewhere, yeah. So that picture I stole from the paper. So that's the efficient frontier. For a particular choice of eta and W low, we will have a straight line that shows us that points on the other side are the only ones that I can realize. Points this side I cannot realize, subject to that constraint. Yeah. So the different constraints that I impose carve out that space in different ways. Yeah, giving me an operable space. The operating space now is kind of here, and in that I fit the next one. Yeah, all that does. Okay, so that's how transaction costs and various things go in, and this Lobo paper discusses this. And I kind of stopped here, and I said, this is one of the big sets of equations that are given in that paper, and the little task as part of your first exercise is to describe this in your own words. Yeah, so that you're not scared by what are the things that are written here, what are these, what are the implications of these, yeah, which is exactly what I just described. Okay. Okay, so now let's do a little puzzle. And the puzzle is as follows. Yeah, no, I don't have to take this away. Yeah. So we have another 5 minutes. Okay. I have set up two portfolios here. So let's look at the second one first. The second one is something from your tutorial. There are, or maybe not from the tutorial. Just I plot some numbers. Okay. I can't plot arbitrary numbers here because the covariance matrix has to be a valid covariance matrix. But I stole it from somewhere else. So there's a 3-asset scenario. I have a covariance matrix and expected returns. I construct another one where I have the 4th expected return. The other 3 remain the same. And the covariance matrix, I have zeros here and zeros here. So all I have done is I've taken this covariance matrix and put 0, 0 here. So I constructed another covariance matrix like this. And then I called these two functions. Okay. And maybe I should do this. See what happens. Yeah, so that's just the program. Stuff there, call the function twice, and then plot what happens, right? Sensible thing to do. And that sensible thing produces this picture. What am I plotting? Where is that? I have solved the Markowitz frontier calculation problem twice, with this one and the other one. And I have plotted one of them in blue and the other one in red. And that's all I've done. So your job is to explain what's going on here. What might this be? So let's have some volunteers saying, what might 0 mean here? So if I construct this one with zeros here, sorry? There is no relationship between the last one and the others. So there's no correlation between the 4th one and the first one, say. Yeah. Okay. What does this mean? 4, 4 being 0.
Yeah, there's no risk on that one.
There's no risk on that one. So the 4th asset that I have added has no risk associated with it. Yeah.
It's like putting your money in the bank for.
Correct. Yeah. So this is like putting your money in a good bank, a safe bank, or buying bonds of a government that you think is not going to crash. Yeah. It's, normally, government bonds are considered risk-free, but some governments more than the others. Yeah. Okay. So yeah. So what I've done is I've included an asset that is risk-free into this portfolio. Yeah. So one of them is totally risk-free. And it turns out that risk-free portfolio, the effect of that risk-free portfolio, effect of including that risk-free asset into my portfolio produces for me an efficient frontier that looks like this. Yeah? And this has nice implications. So suppose you are here at this corner, down here. In this corner, I'm not investing any money into the stocks. I'm keeping all my money in that government bond. Yeah? And my return is 0.1, and the variable risk is 0. Okay? If I'm at this point where it's tangential to this one, I have not put any money into the bond. I have put all my money into the stocks. It has to be, because otherwise I can't sit on the red line. Yeah, the red line is a solution for the optimal portfolio where you are investing all your money in those three assets. Okay? So then along this line are ways in which I can offset, I can reduce the risk, yeah, by investing a little bit of the money, keeping it risk-free. Yeah? That's the idea of sitting on this line, that I have a certain amount of money. I would buy for part of it this portfolio in the right proportion so that I would stay here. And the remainder of the money I would throw it into a risk-free government bond of some sort, so I'll be here. Okay, so the weighted sum of those two, zero risk and the portfolio risk, would take me on this blue line. Okay? Think over the weekend, this can either be enjoyable or drive you nuts. Why I think this line is actually tangential to this. Why can't this blue line cut here, for example? Okay, so that's the homework for you over the weekend. If I disturb your sleep over this, then I'll be very happy. And we'll discuss this on Monday. Okay?